Hello everyone, welcome back to the channel. This is Dr. P Aerospace, and today we're going over our third example problem with conservation of momentum. And this one, honestly, the concepts are not going to be anything too new. The only, new concept in this is the use of polar coordinates, and that's a hint. In case you wanted to solve this by yourself first, which I would highly recommend. But polar coordinates are a bit tricky, and I'm not going to go over every single detail about them, but I am going to show, how this problem would incorporate them. And we'll find that out once we start getting into the question itself. But before we do, I would like to ask if you're watching this video and you get something out of it, please leave a like, subscribe, and comment. It helps me grow the channel, and it also helps me get feedback. So if I'm doing anything wrong, or you want something else, recorded in the future, all that feedback I can take and hopefully cater this channel appropriately. So yeah. Anyways, let's get into it. A small circular object is placed in a 0.75 meter diameter wind tunnel for aerodynamic testing. The upstream and downstream pressures can be assumed to have a uniform distribution. The upstream pressure is 30 millimeters of H2O gauge, the downstream pressure is 15 millimeters of H2O gauge, and the mean velocity is 12.5 meters per second. The velocity profile of the exit is linear and varies from 0 to the maximum at the tunnel wall. Part A, it's calculate the mass flow rate. Whoops. B, find the max velocity of the exit, and C, find the drag on the object. We can assume that there are no viscous forces. Okay, so it's a pretty lengthy word problem, but ultimately this is kind of what we're dealing with here. We just have a wind tunnel here with an inlet and an exit with a constant area, and we have a little object here, which we're going to try to find the drag on. So first and foremost, let's just go through our step-by-step assumptions. So let's write this out here. Just like that. So it doesn't say we're unsteady, and it's actually giving us a mean velocity here. Mean is more like a time average velocity, and that can be assumed. We can, or I should say, we can assume from that we are in the steady flow assumption. So we can write that down here. And next, normally we would immediately go and say, oh, it's incompressible flow. But I want to just kind of take a second and kind of reflect here. The working fluid here is wind, which is a gas, which means that technically we can be compressible as well. So in a more practical scenario here, you actually want to make sure you are in the incompressible flow regime before you make that assumption. Because if you were compressible, you'd have to deal with some modifications to your equations, and you will get an incorrect answer. So just something to be aware of. So this is indeed incompressible flow, and I'll explain why in a moment. Just like that. So we're incompressible because our Mach number of the flow is actually going to be less than 0.3. And this is the golden criteria for determining whether you're incompressible or not. And some people may argue this value, some super nitty-gritty fluid mechanic scientists, but I believe in most textbooks and classes they teach Mach number less than 0.3 is incompressible. So you can cross-check this, but if you're not familiar with Mach number, it's just equal to your velocity divided by your local speed of sound. And this is going to equal to velocity over the square root of gamma RT, and speed of sound in this case is equal to the square root function here, where gamma is the specific heat ratio of air, which is 1.4. R is the specific gas constant of air, which should be 287 joules per kilogram times Kelvin, and T is Kelvin. So if they give you Fahrenheit or something, I would recommend converting everything into metric units just because it's much easier to work with in a cleaner format. But if your Mach number again is less than 0.3, you are good for incompressible flow. So just want to make that apparent because you shouldn't blindly assume incompressible, because if you aren't, you'll get the incorrect answer. Okay, next we will work on our free body diagram here. So let's see here. We have pressure as our inlets and exits, so we can quickly write our pressure forces here. We're going to choose orange. So I'm just going to kind of write a bunch of arrows showing we have a uniform pressure distribution over our inlet. And this pressure force will be equal to P1A1. And similarly, at our exit, we will get a uniform pressure distribution acting to the left here. And this will be P2A2. I'm not going to put a negative or positive on that for now. I'm just going to state that that is a pressure force that's just acting to the left. And similarly, we are asked to find the drag on this ball. Now, one thing to note about conservation of momentum and the way we do this force balance is that we're actually going to be finding a reaction force on this object. So the reaction force will be pointed to the left, but our drag will be pointed to, I'm actually using a different pen here, we'll use green. Our drag will be pointed to the right. So technically, what we're solving in the conservation of momentum force balance is for Rx, but our final answer will be the opposite of Rx, pointed to the right, because drag is going to always act in the direction of the flow. So, for the purpose of this discussion, I'm going to write it out as Rx, and then whatever we get for our final answer, we're going to flip the sign and, direct it the opposite direction, because that's always where drag is acting. So just wanted to make that clear. So that's pretty much our free body diagram here. We have, ultimately 3 forces that we're going to solve for: P1A1, Rx, and P2A2, and that will give us our drag eventually. So that's great. And I wrote Rx here, but I want to make something clear. We are going to be using polar coordinates. So technically, this will be the z direction. And if you're not familiar with polar coordinates, we have the z direction to the right and left. This will be positive to the right. And the radial direction going upwards, because this is a pipe cross section here, right? So if we look at the pipe here, okay, so the center of the pipe, center line right here, this is the R radial direction, and then we have technically theta in 3 dimensions going into and out of the page, and then we have the z direction, which is kind of like the length, axial length of the pipe. So these coordinates are specifically meant for, circular based systems, and they work very well for pipes. So that's why we're going to use the polar coordinate system here. It's much easier. And if you're confused about this, again, I would recommend maybe a different video. I don't have anything currently set for this, but I'm going to do my best to explain the directionality and how we apply it to this. But just kind of showing you the general coordinates here. R is the radial direction, theta is the angle around this pipe in 3 dimensions, and z is the axial direction here. So when we look at kind of a side cross view of our pipe, this is what we're looking at here, where we're looking R is going up and z is to the right here. So yeah, let's start off by solving conservation of mass, because we have our inlet velocity, which they give us as 12.5 meters per second, but we need to solve for V2 max. And I'm going to skip over part A for now, which is calculate the mass flow rate, because you can do this, but ultimately we're trying to work towards our final answer, which is calculating the drag on the object. So if they want you to specifically calculate this on an exam or a homework, you can do it. But for this problem, we're technically solving mass flow rate indirectly with our step-by-step approach. So let's solve for the max velocity. Okay. So, conservation of mass. Let's write it out from the kind of original form that we had with our control surface integrals. So this was surface 1. And the reason I'm doing this is because we're going to have to do some integration. So this will be V1. Trying to remember for a second, don't want to mess this up. Haven't written conservation of mass out in a little bit. This will be plus control surface 2. This will be rho times V2 dot N2 times dA2. just like that. So the good thing is that we are in the incompressible flow regime, so we can immediately make some simplifications here by taking out our density, which is great. And then we can start writing some stuff out here. Give myself a little bit more space. So for our inlet condition, control surface 1, our velocity is uniform. It doesn't vary in the radial direction like our exit does. And nothing else is varying over our area. So we can actually just remove the integration and focus on the dot product in the total area. So in this case, we'll have inflow, which means after this dot product, we'll get a negative V1 times A. And I'm going to write this as like basically, A1 is equal to A2, which I'm just going to say is equal to A. So I don't have to keep writing like, A1 versus A2, etc. So I'm just going to write this as A for now. And then for our second control surface here, we're going to have the double integral of, this is going to be outflow, so we're going to have a positive V2 here. This will be V2 times dA. Technically, I'm going to put a subscript 2 just to, make it clear, but know that A1 is equal to A2. We just have to do an integration here because our velocity is varying over our control surface here. So how do we actually solve this integral here? Well, you'll see that, normally we could just plug in a velocity value, but in this case, our velocity is varying in the radial direction. So that means we actually have to come up with a function for our velocity as a function of the radius of the pipe. So we can come over to the right here, and I'll use a different pen color. Maybe let's use, I like green. We'll do green for now. So let's do maybe a little boxed out area over here. So if we recall, very simply, the slope of a line, y equals mx plus b. In this case, our function that we want is velocity at our exit as a function of the radius is going to be equal to the slope times the radius plus b. Okay, and then we can input some boundary conditions here to solve for m and b. B should be 0, but I'm going to prove that really quickly because at r equals to 0, we get that v2 is equal to 0, as they say in the word problem here. And that would basically mean that b is equal to 0 when you plug those into our equation above. So that's great. B is gone. And finally, we have at r equals to the radius of the pipe, which I'm going to write as capital R here, v2 is equal to v max. I'm just going to vote v2m, just so it's a little easier to write there. And this would mean that once we solve everything, m should be equal to v2 max all divided by capital R. Which means when we plug everything back in, we see that v2 as a function of r is equal to v2 max divided by capital R times lowercase r. So that is a nice little relationship we have here. And now we can just plug it into the v2 in our integral and begin solving it. So let's start off with that. I'm going to move this over to the other side of this equal sign here to make it positive. So this will be v1 times a1. That's going to be, I'm going to move this down a little bit actually, give myself some more room. And now comes the second confusing part for a lot of people. This will be, we'll plug in v2 here. This will be v2m over r times little r. I'm going to make these parentheses a little bit clearer to show I'm just putting in v2 substitution. So now this is where a lot of people get tripped up, and this is going to come down to how comfortable you are with the mathematics, because we're integrating in polar coordinates, which means that we're integrating over either the r, the z, or the theta direction. Now, in this case, our velocity is not varying in the z direction. It may look like it is, right? Because you're saying, oh, well, it's, the velocity here is, pushed up farther on this line in the x space, but that's not how we want to view this right now. our velocity is varying in the radial direction. As you go farther up in the radial direction, your velocity is increasing. This line here is not meant to be like a spatial line. It's just indicating that your velocity is increasing linearly as you go outwards. So we're not varying in the z direction. Now, if we think about this from a three-dimensional perspective, because we're dealing with the area here, we are dealing with a theta term, because technically our velocity is basically, this profile is rotated 360 degrees around the control surface of this exit. So we'd almost get like a V-shaped conical profile at our exit. And that's going to be kind of challenging to draw, so I'm not going to try to draw it. You know what, maybe I'll try to draw it. We'll see. Let's see if this adds to the confusion right now. So let's see here. We have our, I'm going to erase this really quick. Let's see if we can make this less confusing and try not to confuse everyone in the audience here. So we have our center of our pipe. We have kind of this velocity profile going out here like this. Right? This profile is rotated around in three-dimensional space, right? By theta. Technically, by 360 degrees. And that would give you kind of like a, again, conical V type surface there. So that's what I was indicating by that. So we're not varying in z direction, but we do have to consider the theta direction in order to get our full mass flow rate through that control surface there. So we have to vary from 0 to 2 pi, or in other words, 0 to 360 degrees, but we always write that in radians when doing this kind of calculation. And then our radial profile here varies from 0 to the radius of the pipe. And you might be saying, oh, well, why are we doing it from 0 to r? Why not negative r to r? That's because we are technically rotating this profile 360 degrees. So, we go from 0 to r. Whoops, did not want to do that. Oh well, profile's gone. But we're going from 0 to r. When we rotate that 360 degrees, we're going all the way around. So there's not really a negative r per se that we have to consider. That's just kind of how this polar coordinate system works. Now, I feel like I'm rambling a lot here. Whoops, that was weird. My tablet went haywire. But again, rambling a little bit about polar coordinates, but trying to show you the basics in the hope that you can go dive into this in a deeper level, maybe with another video or in the textbook somewhere. But the next step is finding our bounds of integration. So this is dA2. Now, I'm just going to keep this simple. For when integrating, in this kind of scenario over the radius and the theta direction, your dA is r dr d theta. I'm not going to go into the explanation right now, but that's something that I've just learned to memorize at this point when dealing with polar coordinates for pipes. dA is r dr d theta. It ends up working itself out. Again, not going to go into the details because that's out of the scope of this question here. Anyways, we're going on a little bit of a rant here. Let's just start solving this integral and move on with our life. So let's rewrite this out here. This is going to be a very math-heavy tutorial, as you can tell. So we're going from 0 to r. We can take out our constant v2m over big R, and this will be times r squared times dr d theta, just like that. And we can perform this integration really quickly. Definitely going to have to use a couple more slides here. This will be v2m over big R times, this will be, the integral of r squared with respect to dr divided by 3. And we're integrating from 0 to capital R, and this is all times d theta. Okay, so I'm going to write the answer for this on the next slide, just because we're running out of space here. But once you evaluate this, basically, you'd be left with capital R cubed divided by R. So we can take this R out of the bottom, and you're left with a capital R squared on top divided by 3. So let's write that out on the next slide just to make it clear. So this will be equal to, remember this is v1a1, we're solving the right-hand side of this equation. This will be equal to your v2, integral 0 to 2 pi of v2 max, I'm just going to write that as m, divided by 3 times r squared, capital R squared, d theta. And now it should be pretty simple. So from here, this would just be, you know, just multiply by 2 pi basically. This is very basic integration. So this final answer would just be 2 pi over 3 times v2 max times capital R squared. This will be v1 times a1. Perfect. And then from there, we can, I'm just going to use the rest of the space here just to make life easier for us. We can solve for v2 max. That's going to be equal to v1 times a1, all divided by capital R squared, or radius, times 3 over 2 pi. So our area, I'm going to quickly write this out, and I keep writing a1. Technically, a1 equals a2. This is equal to pi over 4 times 0.75 meters squared, and that should be equal to 0.4418 meters squared. So if you plug in, this is 12.5 meters per second. We just calculated area, and our radius is simply, 0.75 divided by 2. Plug everything in, and you should get a V2 max is equal to 18.75 meters per second. So technically, that solves B, but by solving this conservation relationship here, all you really have to do is, just do m dot equals to rho 1 v1 a1, and you can get a solution to A. And I did not calculate that because I didn't find it necessary for calculating the drag on the object because it just was kind of like an additional step I think the textbook wanted. But you can do that for yourself if you want to. I did not end up bothering with it. Okay, let's give ourselves a fresh new slide here to work on conservation of momentum. Now, for conservation of momentum, let's kind of write out our core equation again. Just like this. Let's see here. We can write the summation of our forces in the z direction because, again, we're doing a balance in the axial direction, which we denoted as to the right being positive. So summation of forces in the z direction is going to equal, typically we have an unsteady term, but because we're steady flow, we don't need to worry about that. So we can just worry about our two control surface terms here, which will be surface 1. This will be Vz times rho V1. Technically it's V1z if you want to be more specific. Times rho V1 dot N1 times dA1 plus control surface 2. This will be V2z times rho V2 N2 times dA2. Okay, lots more integration moving forward. Again, feel free to skip ahead if you need to. I'm going to work through the math just because math's important and got to make sure your steps and your signs are correct. Okay, so how do we want to start this off here? Well, let's start off with the easiest part, which is the left-hand side of the equation. So rather than redrawing all of our forces here, which, to be honest, I'm just going to redraw it just because it's easier to reference here. We had a pressure force acting this direction on this surface, which is positive P1A1. And then we had our pressure force acting to the left here on this control surface, and that was, we're going to add a sign here now. This is negative P2 times A2 because we're acting in the negative Z direction. And then we have our reaction force here that we're calculating, which will eventually give us our drag, but we're going to calculate reaction force, and the opposite of that will give us our final solution for drag, because Rx equals to drag. Or I guess we're going to call it like negative drag, or if you want to call it negative Rx equals to drag. Yeah, something like that. But drag's going to be acting in the opposite direction. All right, let's write this out. So we have, let's see, P1A1 minus Rx minus P2A2 equals, because our inlet condition does not have anything varying over the inlet area, that means that we don't have to integrate here. So we can go piece by piece here. V1z, that's very simply just 12.5 meters per second. I'm just going to write that as V1 for now, because V1 only travels in the z direction. And it's positive. This term is positive. We have a density. We have an inflow here, so technically this is going to be negative V1, right? And then times A1. So rewriting this entire term here, we would get negative V1 squared times rho times A1. Great. Now we get into the less fun part, which is the part where we need to do some integration here. So our bounds of integration are actually going to be the exact same as on the previous slide. So this will be 0 to 2 pi, 0 to r. And now we're just going to plug in our values for, you know, this flux term. So V2z is simply this equation here, V2 of r, which is V2 max over the radius times the little r, which we will write over here. So this will be, let's make sure I'm not messing any of this writing up here. This will be V2 max, all divided by the radius times r. And technically, that's our first term. But our second term, if we plugged that value in and then did the unit normal vector, we'd get the same results, but it would be positive because it's outflow. So technically, this quantity would just be squared, because this first term is positive, it's going to the right, and then this term, we have outflow, so this dot product would yield a positive value, so we have basically our velocity squared, multiplied by rho, and then remember, dA2 is just simply, let's see, I don't know why it skipped ahead there, this would just be r dr d theta, because when we're integrating from 0 to r and 0 to 2 pi, this is what our differential area can be represented as. And again, please check out a different video or a textbook if you're confused on that. I'm hoping to come out with a more in-depth video once I get into differential analysis. Okay, so without, oops, did not want to do that. Without going, crazy with the rewrites, I'm just going to focus on writing out this integral, and then we'll combine the full equation afterwards. So for now, we're going to put this on pause, and then we're going to focus on the integral. So we're going to write this, let's write this over here. Maybe I'll write this in I'll just keep writing it in green, honestly. Hopefully that's going to be clear. Just to show that we're only focusing on the integral. 0 to r. So this will be V2m over capital R times rho. And then this will be, we can group this r and the r squared. And technically all these values are squared. Don't want to forget that. This will be r cubed and dr d theta. Step-by-step approach. Again, feel free to skip ahead. I am working this out to make sure no one is confused here. This will be V2m squared over r squared times rho. This would be r to the fourth if we integrate r cubed with respect to r d theta. And if we simplify this, we should get 0 to 2 pi of, so let's put the rho out front just to make it easier here. This would be V2m squared, all divided by 4 times r squared d theta. And then this last part here is pretty simple. We're just integrating from 0 to 2 pi, so this ends up looking like rho times V2m squared times, let's see, this will be r squared times pi, all divided by 2. And that is what this integral is. So let's go to the next slide, and we can rewrite everything out here nice and neat. So this is going to be, I'm just going to start off with drag onto the, or I should say our reaction force will be Rx plus P1A1 minus P2A2 equals, just going to go back and make sure here, set Rx is negative, just to confirm that. And then we have minus V1 squared rho times area. I'm just going to keep writing A1 just for consistency at this point, I guess. And then our solution to the integral, which was rho V2m squared r squared times pi, all divided by 2. Okay, we are almost to the finish line. Sorry if I just blew out your eardrums there. That was a big sigh. 30 minutes in, my hand is cramping. Okay, so let's solve for Rx. We can put Rx to the other side and just kind of move these terms over here. Just do a swap of signs. So we have Rx is equal to, so it'll be P1A1 minus P2A2 plus B1 squared rho A1 plus, this will be minus rho V2m squared r squared pi divided by 2. Oh my goodness, we're almost there. Okay, so that's our final form here. So now we have to convert, unfortunately, P1 gauge, which is 30 millimeters of H2O, which is going to be equal to 294.2 pascals. And then we have our gauge pressure at our exit, which will be 15 millimeters of water, and that'll be 147.1 pascals, just like that. Okay, and then I think we're pretty much good to plug and chug at this point because we have everything. So I'm not going to do the full write out of all the maths here because my hand is getting a little tired. But if you, oops, there we go. If you plug and chug appropriately, we'll see that, P1 gauge we have, area we have of our pipe, we have P2, A2 is just equal to A1. Density for air, I'm going to write that down as well. That's going to be equal to 1.225 kilograms per meter cubed. So we have that. We have our inlet velocity, which is 12.5 meters per second. We have area, density, velocity, radius, and yeah, we should be good. So basically, plug and chug all of our known values, and you should get Rx is going to be equal to, let's see, quick calculation here, should be equal to 54.4 newtons. Now, again, going back, this is the reaction force. It's asking for the drag. So drag is going to be acting in the opposite direction here. So technically, the drag is going to be equal to 54.4 newtons acting to the right. So this would be an acceptable answer for your submission. Okay, so that's it. If you stuck with me for this long, that's crazy. This is a lot of talking and a lot of yapping. I would recommend putting me on double speed for future because, again, I'm going through every single step to make sure we're not missing any signage issues or any calculation errors. I say that, but, if I make a calculation error, please let me know in the comments below. Anyways, thank you so much for watching. Again, quick reminder, if you got this far, give a like, give a little subscription, and leave a comment if you wish. And I'll catch you in the next video. Good luck studying.